Okay, so this is lecture 2 on the gas laws, and the first thing I wanted to do is mention to you, hopefully some of you got a chance to print off this worksheet. This is going to be tonight's homework, and actually probably have an opportunity to finish a lot of this. We're going to do the example as part of our notes. So if you did print this out, and if you didn't, if you can't, it's not a huge deal. But if you did print this out, then you're going to be doing your little drawing of a manometer here and your calculations right there for the notes that we're going to give. And I'll make reference to that. This is the example on the front side of the worksheet. There is something I wanted to point out to you, and that is these significant figures are not always the same with your initial number. So you do want to be careful with that. This has 3 significant figures. This one has 4, and especially one like this is very limiting. That's only 2 significant figures. That 0 is not significant. There's no bar over it. It's not 2.10 times 10 to the second. So that means your answer can only have 2 significant figures. So I did want to point that out to you. And then when we talk about open manometers, that will be the back side of the worksheet. And this will be our second example. So you can write that right there on the worksheet for your notes. And like I said, then you have them all in one place. When you're doing these problems, okay? So I did want to make a reference of that to you. So now let's go back to our lecture and talk about what these manometers are. Physically, how do we use these devices to measure for pressure? So, not quite sure what that sound effect was. I don't know if you could hear that or not. But this manometer problems. All right. So if you could take any liquid and put it in some type of tube, if you were to increase the pressure on the liquid, and of course that pressure would be the gas, because the liquid itself doesn't compress. So because of that, the liquid goes and can change the level. And then you can measure the difference between the levels. And that's what a manometer is. I actually would prefer if you continued your classroom notes, and I'll tell you when to switch to the worksheet. You can put this diagram if you want. It is a good intro to it, but not 100% necessary to have in your notes. And certainly not this one. This is a schematic of an actual functioning gas pressure where they're refining petroleum products, and they really have to monitor the pressure very carefully. So you can see right here 4 manometers are hooked up to check the pressure in various areas. So interesting application of this. But we used to have one of these back in my day when we started back here in '94. We had a mercury manometer. Real dangerous thing to have laying around in a high school. We're proud to be mercury free right now, but we had lots of mercury. I used to pass a bottle around to show how dense it was in class. But then it was found that it causes permanent nerve damage and kind of makes you a little weird after. What was I talking about? Oh, the manometer. Okay, so this particular one's closed. So any pressure that you have is going to push down on this side harder, and then you could actually ours actually had a meter stick, and ours was like a meter high, just chock full of mercury. Just awesome. So that's what this device is. So before we jump in and do the problems, let's do a quick review of the type of gases we're going to be talking about. There are certain monatomic gases, also known as the noble gases. So make sure you get these in your notes. These are the types of gases that we'll be talking about, and you do need to know that those are the noble gases. So you're becoming familiar with the periodic table is going to yet pay off for you again on these units. The diatomic gases. Now, we had talked about the Magnificent Seven, where you start on element number 7 and you make a 7 out of 7 elements. We actually are only going to talk about the Magnificent 5 in terms of gases, that being hydrogen, nitrogen, oxygen, fluorine, and chlorine. Now, I can't ask you this question at home and have you answer it directly, but I want you to think about that. Why is it only 5 instead of 7? See if you can think of the correct answer for this. And the answer is that iodine is a solid at room temperature, and bromine is a liquid at room temperature, so they're not gases. So therefore, 5 diatomic gases. Hopefully you know the formulas of all these. Little self-check here. Ammonia. You should be able to write the formula for that. We did the shape of it. We talked about it in our balancing chemical equations. So it's NH3. Methane, if you don't know this, my heart is broken. CH4, the simplest hydrocarbon. And you will also, we'll leave ethane out of the mix because it's just not very common, but propane, definitely want you to know C3H8. And if you remember, you take the number of carbons, double it, and add to C3H8. So we've been down that road before. So butane was the one that was 4 carbons. So see if you can think of the formula of that. Boom, C4H10. So all of those in this gas unit, I would expect you to know the formula. If I say butane, you need to know that's C4H10. How about something like this, diphosphorus pentoxide? Well, you might not have that memorized, but you don't have to, because diphosphorus means 2 phosphorus atoms, and pentoxide is the 5 oxygens. So you might see something like that, P2O5. But we're not going to spend a lot of time going back and reviewing that anymore. You need to know those gases. This will apply when we do Dalton's law. This will apply when you're doing these manometer problems. Okay, so now to your worksheet, if you have it. If not, this is the time to start with a brand new sheet of paper, or start at the top of a notebook page, because you will be submitting this as your manometer problems, okay? And do as a final format, including the example problems, okay? So the example problems, if you were able to print the worksheet, will be the ones right on the top, right underneath where you wrote your name, okay? So how do we do this manometer problem? Well, this problem is a closed manometer, and to represent the closed manometer on these graphics, I'll use a little rounded thing. You can just simply draw a line straight across on your notes, because you don't have a black and white background like this. But the gas that you are going to be testing, if you know the gas, you have to put the formula here. In this particular problem, it said, a gas with a pressure of 195 millimeters of mercury. So, but if you know that, you have to put the formula. That's why you need to know the formulas of those gases. So, because it's closed, this has 0 pressure, and it'll always be lower on the side with the gas, and the difference in those levels will give you your millimeters of mercury. Okay? So the difference between those two lines will give you your millimeters of mercury. So again, you might want to write that down. Chemical formula, if known, goes inside there. So this is example problem. So you have to include a tiny little drawing on all of these problems. So you're going to be doing this drawing of a manometer 10 times, just to be very clear on that. You're going to lose a lot of points because you got to show where the levels are. When it's closed, it'll always be oriented like this. Lower on the gas side, higher on the closed end. Okay? So let's go ahead and crunch the numbers right now. They didn't ask for millimeters of mercury. They asked for kilopascals, but you have all those units, and I said we could use them as a unit conversion. There you go, 760. Use the bar. Much easier than doing scientific notation on your calculator and everything. So use the bar over the 0. 760 mmHg, 101.3 kPa. And then those millimeters of mercury will cancel out. You crunch the numbers, and of course it's going to be 3 sig figs. 4 there, 3 there, 3 there. The least number will determine that, and you get 26.0 kPa. Put a nice box around that final answer. That's a manometer problem. Okay? And actually the front side of the worksheet is fairly straightforward, but I have to be able to read these things. Take your time. It's not a race. Go for high quality on this one. Okay, now the back side of the worksheet talks about looking at methane. And this is really important because if it's open, which is what this is showing, that means it can be like this or it can be like this. And it said it was 60 millimeters higher on the end that is attached to the methane. So the way that you draw this, and you got to darken that in so I know where the mercury is too. You can't just draw lines all over that. It'll be very confusing. So darken it in. Show that you know where that mercury it is. We know the formula, so you're going to put that in there. And then it's 60 millimeters of mercury higher on the one arm. Now, this open problems will always be accompanied with an air pressure. Okay? So the air pressure is 98.0 kPa, a little bit below normal, which is 101.3. And then we can move on to solve the rest of the problem. So what we notice at this time is the methane has less than 98.0, okay? Because the air is pushing harder than the methane. That's very possible, hint, hint, on 2 out of the 4 problems that you're going to be doing, where it would be like this, where it would be higher on the arm connected to the air. So that would be a little different scenario. But we now know that it will be less than the air pressure. So we got to do a little conversion. We have to take that 60 millimeters right there, okay, and we have to convert that into kilopascals, okay? So the 60 millimeters of mercury, 3 sig figs, boom, do your crunching. 8.00 kPa. 8.00 kPa. You got to have the 3 sig figs on that. Okay? Now, since it was less than the air pressure, and you've now got it in the right units, which is kPa, you can take the 98.0 minus 8. Now, little sig fig hint here. This is one place to the right. This is 2 places to the right. When you're subtracting, you can go the least of those values. So since that's 1, my answer can only go 1 place to the right. So when you subtract 98.0 minus 8, the answer is 1 place to the right. And you don't have to use any bars because zeros on that side are significant automatically, and that is the correct answer. So you can do the rest of these problems on your own now. And good luck.